Right now, neutral atoms are probably the hottest shit in quantum computing. Everyone is looking into that and trying to understand if it's going to be the future, if this is going to be the leading and winning technology. You see that even major research labs, like for example the Google Quantum Lab, is now opening a second branch where besides the superconducting qubits, they are also looking in neutral atoms as of to their last biggest announcements and presentations. So what is actually behind that, and what are the companies that are playing a role here? Well, I mean, we have featured some of them in the Hidden Quantum Champions already, but today we are looking at Planqc with a C at the end, so Planqc, which is another company in this space based both in Germany and in Austria. And we are trying to understand what they're actually doing and how their system works and why this might be the next biggest thing in quantum computing. So if you're interested in learning more about this neutral atom quantum computing company, then stay tuned for today's video. If you want to understand what differentiates them maybe from others and what trajectory they are on right now, this is the right video for you. So stay tuned as we are diving into Planqc with QC. So here we are on their website. It says making quantum matter atom by atom for industry, science and society. From lab to impact, what's happening at Planqc. So you see different announcements here. Meet women in quantum software, 2.3 million funding for hybrid quantum classical solutions in industry optimization, and many, many more of these articles down here. We're not going to go through all of them now. The future of industry is powered by quantum, and I mean here we see again the typical target industries. We see the financial services where there have been already some pretty, let's say, big announcements of where this is being used and banks that are actually working or starting to work with this. But we also see other industries like, for example, pharma and chemicals. So everything that is using quantum computers and quantum physics to simulate or emulate the quantum nature. But we also see other ones like, for example, artificial intelligence that is more on the algorithmic side, using the great power of the Hilbert space to actually store a lot of state information and thereby build these artificial intelligence approaches. We see aerospace, automotive, energy and climate, logistics and mobility. So just one thing, traveling salesman problem, and the security sector, of course, as well. Now, there are also some, I think, case studies down here. So you see quantum computing, enhanced battery innovation, better aerospace materials with quantum computing. So both of these are in the material space. We see quantum-inspired quality control for rocket manufacturing, quantum machine learning for improved climate modeling, and then faster routes, fewer emissions, optimizing logistics with quantum. We also see some partners down here like the Max Planck Foundation, the DLR, which is the German Aerospace Institution, Munich Quantum Valley, the DLR Quantum Computing Initiative, Define as a consulting company that is very heavily rooted in the space of let's say, natural sciences, and many more. Now, further on, it says technology at scales. That scales, our quantum computers use neutral atoms as qubits, the most promising path to fault-tolerant systems. Trapped in optical lattices, these identical atoms remain well isolated, ensuring long coherence times and high-fidelity operations at scale. Ideal properties for building large, reliable quantum systems. One step back before we are moving on here, a quick note on this. So this is basically referring to the comparison to, on the one hand, solid state systems. So if you are, for example, looking at superconductive qubits, they also behave like a single quantum particle, more or less. And that's because of the superconductor, which can be described by a single wave function, which has to do something with the Cooper pairs and the Bose-Einstein condensate. I'm not going to go into all of these details because we're not talking about superconductors today, but it basically is to say that The qubit itself is a still microscopic element, but it is comparatively large. It is constructed out of many qubits, and therefore it is also, let's say, affected by its surroundings, because there's a lot of stuff happening on these silicon wafers. The same is true for other types of qubits that are embedded into solid-state systems. So there's always some interference, and oftentimes the information, the quantum information, is stored in an electrical state. So it is very prone to charge noise, and the way that we interact with those systems is by sending signals in and getting signals out. So we are basically exposing them to charge all the time, and there's also, because of the temperature at which those measurement devices and also the signal generators are sitting, there's some randomness going in there. Then you might have other let's say, sources of charge noise that are around that can affect these systems. Now, on the other hand, we have the atomic systems, right? And there, I think here in this sentence, we see both different ones. We see the neutral atoms and the trapped ions, or the ions. Now, what is the difference between those two? So an ion is an atom where you take away one electron, or potentially also more electrons, from the shell. So the nucleus is sitting in the center with the protons and the neutrons in it, and then you have the atoms that are evolving around this as a cloud from a quantum mechanics point of view, or like if you want to think about it on these orbits, they are running around the atom. Now, if you take away one of those electrons, you are basically left with still a positive charge, a positive net charge in the nucleus, but there's one less electron that is balancing this out. So basically you have a positively charged system overall, a positively charged atom, which we call an ion. Now you can use electric fields to change that position. Think about a capacitor where you have a plus side and a minus side. You put the ion in the center, and because it is electrically positive charged, it will go to the minus side. So it will move within this electric field. If you are switching the polarity of those two plates, you're basically keeping the ion in the center position, because it's always like moving slightly left and right. And more or less by this, you can basically trap an ion in the center. But again, the problem remains that even in those ions, we use the electric charges. So we are basically putting electrons on higher orbits to encode information, and thereby we are also becoming, in a way, charge noise dependent. So there is an electrical way to kind of interact with the atom, and thereby you are opening up a new channel for noise to kind of come in. And of course, the same is true for magnetic interactions. If you're thinking about, let's say, nuclei that have a net spin to them. So you have the neutrons, you have the protons, you have the electrons, and they all carry this property which we call spin, which is a magnetic property. And if you sum all of these up, in some cases you end up with something that is relatively neutral, and in other cases you end up with something that has a net positive spin, for example. Now, in a neutral atom, you might still have this spin property. It depends a little bit on which atom you're looking at, but at least if you're looking at it from the outside, it is in itself a neutral system. Like if you're boxing it in somewhere, if you take a single atom, at least it's charge neutral. And that basically helps you to remove a lot of noise from that, which on the other hand also makes it less error prone. Then talking about fault tolerance is one step up. If you're having many qubits, you can run error correction. So you can basically encode your information in multiple qubits by using the principles of superposition and entanglement, and thereby you can kind of remove or correct for certain specific type of errors. But that means you need a lot of these qubits, and they need to be interconnected to each other. And that is something that is done via this error correction algorithms. They're different ones. And that is something which then leads to this fault tolerance. at the end. Now then it says here from hardware to application. So we develop full stack quantum solutions from the ground up and top down, from highly scalable, high quality hardware to tailored algorithms and quantum software. This co-design approach allows us to turn real-world use cases into quantum applications faster, whether as an on-premise system, cloud-based computing, or tightly integrated HPC solution. And also this is something that we've seen before, right? Companies that are offering different, let's say, integration levels, from selling whole systems all the way to basically selling cloud solutions and selling systems as standalone systems, as well as integrating them into HPC solutions. If we are looking at the market broadly, and this is something which we are going to do in our Hidden Quantum Champions learning experience, which you will learn about soon, then actually what we see is that most of the companies go back again to selling hardware and go away from this cloud type of approach, because at the end it of course also needs to generate some revenue. And if you don't have a second, let's say, sales proposition, a second thing that you can sell besides the quantum computer, oftentimes it ends up, from what we are seeing right now, that companies are either selling systems only, or they create a second branch where they sell, I don't know, quantum sensors, quantum communication stuff, or something else that is already easily or easier scalable than maybe a quantum computer is. We also see the full stack claim in here, so basically ranging all the way from building the qubits all the way up to building software algorithms that can then be used in applications. Then, I'm recording this end of March 2026. There's a little news section down here as well. And we see here from 25th of March, so very recently, meet Ada Sorani, Business Development Specialist at Planqc. So you can see, or Planqc, I'm not sure what is the correct pronunciation, but you see it's very much up to date. If you know the correct pronunciation, let me know down in the comments below. Advancing Quantum Together, and then I guess you can meet the team here. So founded in 2022 by quantum physicist Glatzeblatt and Sayer. Planqc spun off from the Max Planck Institute for Quantum Optics at Munich, Quantum Valley's first startup. Our Garching headquarters opened in 2024, houses both our quantum hardware production and software development. Garching, and also especially the Max Planck Institute for Quantum Optics, very well known in the community. Definitely one of the, let's say, probably very science-heavy spaces in the world in this specific technology category. I think also for the Max Planck Institute for Quantum Optics, there were some Nobel Prizes going there at some point. Now let's quickly check out the technology part. I don't want to dive into the solutions today too much, because if you're looking at quantum computing companies, you will see a lot of these. You see the basically industries they are targeting, but what is interesting probably today is to look at the neutral atoms. And I think there's a lot of information on here, so I'm not going to go through all of this today, but just going through a couple of very essential things. So what are the advantages, right? That's what we want to know. Identical qubits, we've talked about that before. Our qubits are neutral atoms that are 100% identical by nature, no fabrication defects, no variability. Okay, scalable by design. Neutral atoms enable quantum systems that scale naturally from hundreds to millions of qubits without architectural bottlenecks. Quick point on that, scaling atoms is probably not the problem, right? Because everything that we are seeing in our everyday life, everything that we can touch, is composed out of millions and millions of atoms usually. So scaling from 100 to 1000 to a million doesn't seem to be complicated, because if you're taking a gas bottle, in there you have many more orders of magnitude more atoms in there. So like getting a million equal atoms is not anymore a technical challenge for us. Now, getting them into a quantum system is a different topic. You need to cool them down. I've talked about that in, I think, even the last video before that one here. So if you haven't seen that, check out the Hidden Quantum Champions playlist. That is challenging, but it's possible. Now, arranging them in a system, in case, for example, of ions, is not super easy if you think about ion traps. For neutral atoms, it's also not super easy, but you can actually use optical tweezers and you can basically arrange them in a lattice type of architecture. And that one you can actually scale because it's basically just taking light and splitting it up into many, many channels. And then basically this light is trapping the atoms in specific positions. So that is possible. But then, of course, let's say manipulating them, doing activities with them, connecting them with each other, doing entanglement, reading them out and so on, I think requires a little bit of work still. So this is not something that like on 2 afternoons you figure out, right? And that's also why we have these companies and why there is funding going in there, because there is also some research work to be done still. Then you see here the flexible connectivities. Atoms can be arranged in large 1D, 2D or 3D arrays and individually manipulated using quantum gas microscopes. So again, these microscopes, they are now the manipulation technology, so they are being used to manipulate and read out. I'm not an expert on that, so I cannot tell you too much about the details. And then 1D, 2D, 3D, right, is on how you arrange those atoms. So there are different ways to arrange them. Every single one of them comes with advantages and disadvantages, as in how you can connect to those, how dense you can actually pack them, how well you can manipulate them, how well you can entangle them with each other. So there are many different things to take into account here. Then you see the fast quantum gates. So highly excited Rydberg states allow fast and reliable 2-qubit gates using laser light. Now, what is a Rydberg state? Maybe a quick point on that. I was talking about the atoms before with the electrons in basically a cloud that is around the nucleus. And in this classical picture, we said they are moving like little satellites around the Earth. They are moving around the nucleus on these orbits. Similar to the satellites that are moving around Earth, there are different orbits at which those electrons can actually move, different trajectories. If you are closer to the nucleus, you have to move faster because otherwise you're crashing into it, right? Which never really happens. But you have to move faster with a satellite if you want to move closer to Earth. So basically the ultimate state is where the satellite falls basically down to Earth all the time, but it's rotating fast enough so that it doesn't hit the ground, right? But then there are also other orbits where you go further out and you can move slower all the way to the point where you have geostationary satellites, which basically stay on the same position because they are far enough, more or less, away from the ground that they don't have to move relative to the ground, which still means they're moving, right? Because Earth is rotating. So they're still on some, let's say, trajectory around the globe. Now, why am I telling that? Because if you're now thinking about those electrons, they are also moving on those orbits. And the difference to the satellites is they are quantized. So there are only specific orbits which you can hit. But they basically are associated with different energies. So the further you move out the electron, the more you have to increase its energy. So if you, for example, hit an electron with an X-ray beam, hit an atom with an X-ray beam, it might happen that you put so much energy in it that the electron just shoots out, and then you have ionized your atom. So that's when you basically remove the electron. But if you have a little bit less energy, it might be enough to get the electron to a very high orbit. So then it stays at this very high orbit, which means also that technically your electron cloud is expanding from very, very tiny spaces all the way to like super large for atoms, super large space. It can go, I think, up into micrometer spaces if you are like exciting it to a very, very high state. So then these electrons, they are moving in this very big, very far out trajectories. This is now in the classical picture. Of course, in the quantum picture, they are wave functions, right? And that basically means your atom is expanding in size, and that's how you can use those Rydberg states to couple two atoms to each other. Because now, if you have a second atom sitting here, and your first one is sitting here, and normally your electrons are very, very close to your atom, and now you're exciting this, you are basically creating a big electron cloud that can even overlap with the electron cloud of the other atom in a way, and that's how you can entangle them. So the second atom here is feeling the electron from the first one, more or less. And then, of course, once the electron falls back again onto its lower orbit, then you might be able to measure that, emit some states, right? There might be some optical transitions where it emits a photon or something like that. I mean, how that works in the details is then, of course, up to the materials that you're using, the atoms that you're using, and of course to the setup that you have. I'm not an expert on all of these details, right? So then you see here the extreme coherence. Atomic qubits are well isolated from the environment, maintaining quantum information for several seconds. And again, here, this is very important to see. Fast gates and long coherence times is exactly what we want to see, right? Because if you have fast gates and short coherence time, it still means that you cannot do many operations, quantum operations, because after a couple of operations, your qubits will basically lose their identity again. That's what we call decoherence. So if you're bringing a qubit to the state 1, let's say you have a spin qubit and the spin points up, that's considered state 1. After some time, because of decoherence, this might start to change a little bit, and maybe at some point it ends up, because of entropy, to be in a 50-50 state where it's either 0 or 1, and then when you measure it, it's not anymore the identity that you gave it at the very beginning, even though you didn't do any operations. That's called decoherence, and that's what you want to avoid, because at the point where you have decohered your quantum information, you cannot really work with it anymore. So you want to be able to have as much time as possible for this decoherence to happen. So it should go as slow as possible. At the same time, you want to have gates that can operate as fast as possible, so that you can do thousands of operations before you actually hit into this natural decoherence limit, which at some point always happens. And that's very interesting, this combination, fast quantum gates and extreme coherence. And it's not the same for all the systems. There are systems that can keep coherence for minutes, but then it's really hard to change the state of your quantum system. There are other ones where the coherence is very, very short, but then you have even quicker control gates, so that you can still run a lot of operations within a very short amount of time. Now let's move back to the advantage points here. Room temperature operation. While the atoms are cooled to ultra-cold temperatures, the entire quantum computer runs at room temperature, no cryogenics required. Again, if you want to learn about the cooling, check out the other video where I talk a little bit more about how it actually works. Low energy consumption, so efficient laser cooling and compact setups make operation highly energy efficient. And this is again comparing to the cryogenics, right? If you're looking at one of these chandeliers that you know from the whole quantum advertisement, these are cryostats, and usually on the lower side they have cooling powers in the milli or microwatts even, so very, very small. If you're thinking about your LED, which might run on, I don't know, 5 watts or 2 watts or something like that, this is a small power consumption. You can run it on your smartphone, right? LEDs are everywhere. But now we are talking about microwatts of cooling power. On the other side of the cryostat, like where actually the cooling on the first stage happens, you're putting in kilowatts of energy. Kilowatts is quite a lot. It's not something that you can just create with your normal plug. So with your plugging in your computer and charging it, it's just a couple of watts. If you use your hairdryer, you might end up going into the kilowatt range, but usually you don't run that 24/7. And then if you are looking at these compressors, they're actually quite energy hungry. They run the kilowatt range. You need like one of these bigger plugs to actually connect them. And then here you don't have that, right? You still have a couple of energy consumption mechanisms. So there are vacuum pumps which constantly have to run to keep, I think, those chambers in this ultra high vacuum state. You have the lasers that need to create those signals. You have all the active components for the optics controls. And then of course the computers that are running all of the signal processing and so on. But still, this is considered to be much lower on operation status than maybe one of these cold compressors or cryogenic compressors. Finally, there's some information here on data center readiness. So their computers are built to integrate seamlessly into modern data centers. And that probably refers to the form factors, as in they have squeezed the optical table that they need to do all of these optical stuff like laser beam splitting and deferring and mirrors and all of that stuff, lenses, into a shape that fits into a typical data center rack type of architecture. Then there's some more information here, some more about the use cases, but I'm not going to go into that. Let's quickly check out the platform as well. So there's an operating system for quantum operating system layer. Our quantum operating system layer provides the foundation of running quantum applications efficient across varied hardware environments, including low latency control and scheduling of quantum programs, resource management and user access control, compiler interfaces and error mitigation tools, and then we also see the integration with simulation environments and hybrid classical quantum workflows. All very important components. Just very quickly, so low latency control and scheduling of quantum programs refers to how these lasers have to be activated, turned on, turned off, right? Like the sequences that are basically the encoded version, like the low-level hardware version of your quantum algorithm, which also leads to the other one here, which is the compiler interface, right? What does the compiler do? So you come with your idea of which algorithm you want to play on your gates, like do a CNOT gate here, do a Hadamard gate here. If you don't know any of these, it's not important. It is basically the same as the logical, or it's a quantum version of those logical gates that we know from classical computing, NAND gates, OR gates, and so on. There are also quantum gates, and in a very, let's say, low-level algorithm point of view, you want to be able to have those gates control your qubits, do something on them, and this needs to be translated into lasers doing specific kind of signals, right? But then also sometimes if you have, like in your scheme, two qubits sitting next to each other, in the actual hardware they might not be sitting next to each other but on opposite sides, so you have to add a couple of operations to make it look like they sit next to each other, even though physically they don't. And then on top there's error mitigation, which is not the same as error correction. Error mitigation is using a knowledge, an understanding of the system architecture or the system behavior itself to mitigate errors. Error correction is using an algorithmic approach that is sitting on top of the system, of the physical system, to remove actively errors or to correct for errors that are accumulating during your operations. Then we see here the resource management and user access control. I think that's kind of clear. Like if you have multiple users, for example, via a cloud that want to interact with your system, you need to manage that. There's software required for that. And then, of course, here is also some integration with simulation environments and hybrid classical quantum workflows. So simulation, of course, makes sense to compare your system with what you can simulate and also do some easy stuff like dry practice before you then get the wet practice by actually running on the proper system, right? Like in a swimming exercise where you practice outside of the water and then you jump in. So you need a good simulator environment. And then, of course, the hybrid classical quantum workflow is very important, especially when it comes to integration into supercomputing centers, which they are targeting as well. Then you want to combine supercomputers with your quantum computers and have the quantum computer as an accelerator, right? Similar to a GPU, you would have then your QPU, your quantum processing unit, as an accelerator. And this is all, of course, very software heavy and has to be built in terms of software. You see system integration, there's something on the hardware down here, but I don't want to jump in all of these details because I don't want to make it too long of a video. So as per usual, let me also quickly hop into the company itself and talk a little bit about that. So what do we see here? So with neutral atom qubits, Planqc is on the fast track towards industry relevant quantum computers. Planqc is on the one of the leading companies in the development of digital quantum computers, utilizing a unique technology based on neutral atoms as qubits. Planqc is pursuing the fastest path towards building industry-relevant quantum computers. As a full-stack quantum technology provider, Planqc covers the entire value chain from hardware and quantum operating systems to quantum computing applications and quantum-inspired software solutions. And here we see one of those systems. And yeah, as mentioned, you see it has this, let's say, server kind of shape. So it looks like it could go into a supercomputing center right away because it's a standardized shape and size. There's some information here about the company itself. You see that there's more than 80 million euros in total funding that they've secured. It's a very diverse team of 30 plus nationalities with more than 100 people working across R&D, engineering, and business. You see they have 15 plus industry relevant algorithm development projects. So that's on the POCs that they are working on. 3 quantum computers built or under development. So these are, let's say, the production outputs. And then they have 3 locations across Germany and Austria. We will see those different locations in a second. Here, I think we see the founder team, founded in 2022 by quantum physicists Dr. Alexander Glätzle, Dr. Sebastian Platt, and Dr. Johannes Zeyer, as the first spin-off of Max Planck Institute of Quantum Optics with the framework of the Munich Quantum Valley. Planqc builds on internationally acclaimed cutting-edge research. The successful transformation from fundamental science to market-ready products is considered groundbreaking and offers hope for Germany as high-tech location, according to Handelsblatt, which is a German newspaper. This achievement has been honored with numerous accolades, including the EY Entrepreneur of the Year Award 2024, the German Startup Award 2023, and the recognition as a technology pioneer by the World Economic Forum. Here we see the timelines of founded in 2022. 2023 wins a 29 million euros contract from the German Aerospace Center DLR. And also some venture capital, I think, going in, new headquarters and growth. So opens its headquarters in Garching near Munich, launches the MAQCS project to develop 1000 qubit quantum computer for the Leibniz Supercomputing Center, LRZ, and closes a 50 million euro Series A round. And then in 2025, we see the expansion and industry collaborations with Airbus, ESA, Fraunhofer Institute, and Define, the consulting company that I was talking about before, and I think the other ones you might have probably heard about. Here you see again the team, the founders, and then of course there's also board members in here. You see they come from various different backgrounds. I'm not even sure. Can you see the backgrounds here? I don't think so, but here you see the scientific advisors. That's what I wanted to quickly show. Oh, I think you also, I thought I had seen somewhere the different companies they are coming from. But yeah, I think there are like various different advisors and board members from various different backgrounds and industries that are involved here, even though I cannot see it right here. And then maybe I was at a different page before, because I also cannot see the different offices here. There were offices in Garching, in Innsbruck, and then there was one in Erlangen, I think, in Germany. Maybe that was somewhere else here. Contact us. Ah, yeah, here you can see the different. It's Ulm. Sorry, it was not Erlangen. Ooh, bad mistake on my side. So you see the 3 different offices and locations here. And yeah, with that, I think we are already at the end of today's video. I hope you liked it. If so, please make sure to give it a thumbs up so that the algorithm also shares it with other people. If you see the, like, I think it's called hype, also give it a hype if you like the video. Very happy that you joined all the way towards the end to over here. Looking forward to see you in the next video. As always, make sure to stay hydrated and see you then. Bye bye.